It's about time. Let's start with the webinar. First of all, thank you for the kind invitation to present some results from my research. For those who don't know me, my name is Gaston Fermandois. I'm a professor, an assistant professor at the Department of Civil Engineering in Universidad Técnica Federico Santa Maria in Santiago de Chile in South America. The title of this presentation is Advances in Multi-Axial Real-Time Hybrid Simulation. Just before we start, I had a PhD in civil engineering from University of Illinois, where I conducted most of the research that I'm going to show you today. Previously, I got my bachelor and my master's degree from Santa Ana University, where currently I'm working. My research interests are earthquake engineering, structural dynamics, hybrid simulation, structural control, structural health monitoring, steel structures, and structural optimization. And I leave you here my webpage, gastonfermandois.com. And if you have Twitter, I also use often Twitter to post things related to my research. The outline for this presentation, I will start with a brief motivation for the topic at hand. I will describe what multi-axial real-time hybrid simulation is. And then I will split the talk in two sections. One is dedicated to centralized compensation and decentralized compensation. I'm going to explain what those two terms are. And I will end with some concluding remarks. So to start, the motivation, probably you already know that structural performance assessment is key to design reliable structural systems in our built environment. How do we assess performance? There are two ways. First, which is the most common and simple to do, is through numerical simulation. This is an idealized representation of the physical phenomena. It's cost effective because basically you need to buy a good computer, and with that you can run many simulations in a brief amount of time. The problem is that its accuracy is determined by model calibration through empirical observations. A model that is not well calibrated cannot give you good predictions of the phenomena that you want to predict. For that, we need experimental testing. It's the most reliable way to assess the physical phenomena, but it's expensive and limited by laboratory capabilities and constraints like budget and space. If we have enough observations, we can learn from those observations, we gain knowledge, and we can create better predictions through numerical simulation. So this is the reason why experimental testing is so important. The gold standard in experimental testing is shake table tests. Here are two examples of the largest shake tables in Japan and in North America. And you can see in the description of each table, there are several limitations for this kind of facility. So constraints play an important role whenever you want to conduct experimental testing. Those constraints can be laboratory space, loading capacity, payloads, and budget. And that's the reason why hybrid simulation have become a very interesting alternative to conduct reliable and accurate experimental testing through the combination of both numerical and experimental knowledge that we have of the system that we want to study. So hybrid simulation, in brief words, is a substructuring technique that develops two different domains of the problem that you want to solve, and you connect both domains using actuators and sensors, using technology that is available in your laboratory. The advantages of using hybrid simulation is very accurate compared to shake table tests in order to impose dynamic loading, is quite cost effective, and it's flexible and repeatable. We can have one reference structure, and if we want to study the reliability of a particular experimental substructure, we can implement multiple of those experiments to run that assessment. And there are many examples of hybrid simulation in the literature. We have conducted both hybrid simulation using a single degree of freedom interface between substructures and multi-degree of freedoms between substructures. And this is well documented in the literature, and I'm not going to stop here too much. Moving on, the topic that is of our interest is real-time hybrid simulation. What's the difference? Real-time hybrid simulation, the same as hybrid simulation, we have a reference substructure that is partitioned in two subdomains, a numerical and an experimental. The experimental usually is a component that is of our interest, that we want to assess its performance because we identify it as a critical component. So we build it, or we install it in a laboratory environment, and we connect both domains through actuators and sensors, and we close what we call the hybrid loop, where the numerical substructure commands a displacement to the experimental substructure, and we measure the restoring force, and we close the loop in order to conduct the numerical integration. But the difference is that we do this in real time, where the sampling time is of the order of milliseconds. This is ideal to study components that are rate dependent. And there's also a quite variety of publications on this topic. The challenge of real-time hybrid simulation is synchronization. So we're using actuators in order to impose displacements into our specimens. And the problem is that actuators have some delay in the measurement signal compared to the target or the desired signal. If we plot this in time, if we want the actuator to move according to the trajectory in blue, the actuator, due to its inherent dynamics, is going to move as the curve shown in red. And this creates two types of errors when we conduct real-time hybrid simulation. One is undershoot. So basically, we're going to have errors in the amplitudes of the displacements that we want to impose. But not only that, we are also going to have delays. The measurement is going to always be delayed with respect to the displacement, the desired displacement. And this can cause not only loss of accuracy in our experiment, but can also drive the system to behave in an unstable manner. Sometimes time delays are equivalent to add artificial negative damping to the experimental system, and that is not good, especially if we have systems that are lightly damped. So that could cause a huge problem. As an example, this is a numerical simulation where we have the ideal case in the top left corner without any delay. And when we start increasing the delay between those signals, and there are synchronization errors between both domains, we see that at some point, for instance, at 9 milliseconds of delay between both subdomains, the response in the measured displacement is going to render to be unstable, and that is quite a problem. What is the solution to this problem? Through dynamic compensation. And there are a bunch of different alternatives of dynamic compensation that have been studied also in the literature. Currently, there is a benchmark problem in RTHS that faces this dilemma by providing a platform in order to assess different solutions of delay compensation and try to understand what are the advantages and benefits of different compensation schemes. So this is also well known in the literature, and this is something that caught the attention of many researchers in the field. So moving on, there are a lot of reasons for conducting multi-axial testing. And I'm going to classify these reasons in two main reasons. One is that we need to apply realistic boundary conditions over the specimen. This is a picture taken at the University ETH at Zurich, a loading equipment that imparts boundary conditions at different points of the specimen, and you can see that there are a lot of actuators connected to this element. The other main reason is we need to increase the loading capacity of our laboratory. This is a picture taken at the University of Illinois at Urbana-Champaign, where in a test where we have a very stiff, actually stiff element, we require dozens of actuators in order to impose the boundary conditions that we need. So there is a good opportunity in trying to conduct experimental tests with three-dimensional multi-actuator loading assemblies. And this has been done in the past, but in slow speed. For instance, in University of Minnesota, Swinburne, and ETH Zurich, they have this system called the MAST, the multi-actuator system. And in University of Illinois, they have these boxes called LBCDs, which stands for load and boundary condition box. All these systems have the same thing in common, that they have a platform that is extremely rigid, and basically this platform, or this cruciform platform, works like a rigid body. So through the connection of actuators, we can move this rigid body in space, and this rigid body will impose the boundary conditions at one point over the specimen that we want to study. There are multiple problems that require to conduct the testing using the real-time execution of the testing, because these problems may require to consider that the elements are rate dependent, right? So if the elements are rate dependent, and we need to impose a multi-axial loading condition of the over the element, then the previous frameworks that I showed before are not satisfactory, and we need something that will can conduct this kind of test. So this is basically the motivation for the following slides. Before going to that topic, we conducted a literature review on the field, and we identified that in real-time hybrid simulation, there have been some work, or a lot of work, with multiple actuators, but where the actuators were coupled through a flexible structure. We have papers that date from early 2000s to the late 2010s. There was a paper that was published last year about this topic, but this is not the topic of our attention. What we are more interested in is the topic of actuators that are coupled through a rigid link. So basically, this is an element that is extremely stiff, and we have coupling between the actuators that are connected to this element. So the first study that tried to solve this problem was Blakeborough et al. In 2001. They conducted a very simple problem where they had this moment frame, and they identified one of the columns of this frame as the experimental substructure, and they wanted to impose in the boundary one translation and one rotation. This 2 degree of freedom system requires 2 actuators in order to impose this boundary condition. The problem was that when they tried to design the delay compensator for this test, they found out that this experimental setup was highly prone to instabilities. So the ad hoc solution at that point was to artificially increase the numerical damping up to 5% in order to work with these tests and don't have any instability issues. You know that if you add numerical damping too much, probably the response of the structural system is not going to be too accurate because you are considering too much damping, and probably the demands of displacement are going to be too low, or the velocities are going to be too low. Then in 2002, Darby et al. Followed the study from Blakeborough. They conducted an online delay estimation for each actuator. So basically, they incorporated this estimation of the delay in order to include this estimated delay into a polynomial extrapolation interpolation algorithm to try to compensate each actuator independently. The figure on the left shows the delay estimate for each actuator. You can see that at a given time, both actuators don't have exactly the same delay estimate, even though these two actuators are considered to be twin actuators, are almost identical. The other thing that was observed in this paper was that the time delay increased as a function of the specimen stiffness. So not only we have a coupling because of the actuators that are basically battling each other in order to move the prescribed displacement that is supposed to move. Not only that, but the specimen stiffness also play a quite important role in this estimation. Then we have Bonnet et al. In 2007, where they have this experimental setup with 3 masses that were connected with springs. And at the ends of the first and third mass, we have actuators that impose the motion of this 3-degree of freedom system. And they found out when the springs between the masses was selected to be a very steep spring, or basically they were rigidly connected. They find out that there was an undesired high frequency vibration that was observed close to the third mode of this 3-degree of freedom system. That was not the delay compensation they designed was not capable of remove this kind of error. Obviously, this is an unexpected response that could lead to an instability, and this is quite dangerous when you run a test in the laboratory. So to sum up, we have experiences using 2 actuators that are really connected in the literature. But then our purpose is, what about trying to reproduce realistic 3-dimensional motion into a point in a specimen to try to assess the behavior of this specimen? So a rational approach for real-time hybrid simulation that can accommodate realistic loads and boundary conditions is required for this matter. So we proposed a framework called multi-axial real-time hybrid simulation, or maRTHS for short, where we basically have a boundary between both domains that have multiple degrees of freedom at one point. And the main idea is that we're going to close the hybrid loop. Basically, we're going to calculate all the displacements at the boundary from a numerical substructure. We're going to command those displacements over our multi-actuator loading assembly. We're going to measure the restoring forces properly, and we're going to send that signal into the numerical substructure to continue with the numerical integration. Everything is done in a very small time step. So it's basically a real-time system in that sense. In order to avoid any instability and try to get accurate results, we need to design an outer loop controller that is going to be the responsible of synchronizing the signals between the measured experimental substructure and the desired target from the numerical substructure. The methodology in order to conduct this is, first, we need to design the experimental setup, and we need hardware and software capable of conducting maRTHS. Then we need to understand the kinematics of this problem through a study of both coordinate spaces where the system is working. Then if we're going to design a compensator that is based on a model of the system, we need to identify that system. So system identification is a key aspect of this framework. And finally, design the compensator, implement that, and run the test. This is basically the research that I conducted during my doctorate studies. For the experimental setup, we choose the small-scale LBCV box at the University of Illinois, which is basically a 1/5 version of the large-scale load and boundary condition box located in the same facility. These boxes are connected to a strong reaction wall and floor. So basically, the motion of the platform of this box is going to conduct the motion, the relative motion of the specimen in one point, while the other point of the specimen is connected to the strong floor. The nominal parameters of this LVCV is shown in this table, and overall, the displacements in the X direction is, let me choose a pointer. I'm going to use this laser pointer. Okay, so in the X direction, in this direction over the LVCV, we have approximately 2 inches of displacement, and on the other orthogonal directions, we have almost 1 inch. And the forces are capacity 30 kilonewtons, more or less, 46 kilonewtons in the vertical direction. So the experimental setup is as follows. We have a host PC that will hold all the numerical computations, algorithms, numerical substructure if necessary, or communication protocols. And all this code is going to be compiled and is going to be stored in a microcontroller, a real-time system, in order to conduct all the computations at a real-time execution. The controller in this case was a DSpace controller. And the DSpace controller is responsible for creating an analog signal, a voltage, that is going to drive the actuators to move in the axial direction. Basically, it's going to move an extension of the actuator. The actuators are driven through an analog servo controller. So the analog servo controller will send the signal to each actuator, and we will connect the real-time controller to the servo controller in order to send the signals from the numerical substructure. So this is basically the hybrid loop in maRTHS. We send a command in actuator displacement, then we send a command in servo valve current to each actuator. The actuators will move, and then we will measure the actuator stroke, the actuator force. We have each actuator has a load cell that is installed in line with the platform, so we can measure forces. And if it's required, we have external measuring system in order to measure the position in a Cartesian space of the specimen. Moving on, we need to make an important definition to understand maRTHS. And this definition is a parallel manipulator. What is a parallel manipulator? It's basically the load and boundary condition box that we're studying. We have two bodies. One is fixed and the other is a moving body. And both bodies are connected through prismatic joints, or in this case, actuators. So we have N actuators. If each actuator or each joint is extended or retracted, we will have that the moving body is going to have a change in its position due to this kinematics of the problem. So we define two frames. One is called the global frame, which is fixed. And then we have a moving frame, which is a frame connected to the body. And we can, using this definition, we can define the rigid body motion of the moving body with respect to the global or fixed frame. This rigid body motion basically consists in 3 and 6 degrees of freedom, 3 translations and 3 rotations. We can determine the relationship between these 6 degrees of freedoms with respect to the extension or retraction of each of the prismatic joints. So with that, we define also 2 different spaces where we're going to work in maRTHS. The first, which is the Cartesian space, which has all the Cartesian coordinates, 3 translations and 3 rotations, of the motion center of the moving platform, where we connect the specimen, or even the specimen. If we want to control one point of the specimen, that will be measured in Cartesian space. On the other hand, we have the joint space, which is the space where we measure actuator length, or LVDT length, or load, the forces in each of the load cells that are in line of each actuator. So these 2 spaces are located in a different place, and we need a way to try to translate the information from Cartesian space to joint space. That is done through kinematic transformations, and there are 2 important kinematic transformations in this framework. The inverse kinematic transformation to go from Cartesian space to joint space, and the forward kinematic transformation to go back from joint space to Cartesian space. This animation illustrates basically what I'm trying to say. Each extension of the actuator has an effect on the motion of the platform in Cartesian coordinates and vice versa. So it's quite important to try to have a good, accurate way to get this information in order to make accurate estimations of the position of your specimen. So we developed for maRTHS a fast kinematic approach, kinematic transformation approach, to include it in the hybrid simulation approach. So the inverse kinematic transformation, which goes from Cartesian to joint, it's a nonlinear function, but it's explicit, and the solution is closed form. So basically, if we have the vector in Cartesian coordinates and we want to calculate what will be the associated extension of each of the actuators, that is very easily computed. For the if actuator or joint, the extension of the joint is basically the norm of this vector qi, where the norm of this vector is basically the position of the moving body with respect to the global frame, plus R, which is the rotation matrix. Using Euler angles, you can calculate that rotational matrix. BI is basically the position of one of the ends of the actuator connected to the moving body. minus AI, which is the position of the other end of the actuator that is connected to the fixed frame or global frame. So with that, we can calculate the joint stroke. But the forward kinematic transformation to go back from joint space to Cartesian space is exactly the same nonlinear expression. So in order to solve P and the components R that are inside the rotational matrix, you need to solve a nonlinear equation, which is an implicit problem, and the only way to get an accurate result is through an iterative solution, for instance, using a Newmark approach, sorry, a Newton approach or something like that. Since we don't have enough time to run all these computations in order to implement this in real time, we propose a linearized version of the FKT, which basically takes the Jacobian of the transformation from Cartesian to joint space. And using that matrix, we basically make a linearization in one step to get the estimation of Cartesian coordinates given actuator strokes. Okay, moving on, another problem that we face during this implementation is the effect of connection flexibility. And this is quite important in the way that we choose what kind of controller we want to implement for maRTHS. This was first documented by Chang et al. In 2015. Basically, imagine that you have a loading assembly like the one shown in the left. It's basically this box with two actuators. We have a reaction wall that is connects the box, and the specimen is between the moving platform of the box of the loading assembly and connected to the reaction floor. If this specimen is stiff, is very stiff in the axial direction, if we impose a motion of the actuators in order to create a downward vertical displacement of the specimen, what will happen is that the reaction wall can deform. And this was the case in an experiment conducted at the University of Illinois. So in this problem, we can have a situation where the actuator strokes are different than zero. But if you look at the position of the specimen, this specimen practically doesn't move. So there are no direct relationship between the strokes of the actuators and the Cartesian motion, and that can cause a problem, especially related to what I explained before, according to these kinematics. So there's a solution to avoid these problems is through the use of an external measuring system. So in our study, with the actuator strokes that were measured using LVDTs, we added linear potentiometers, like these ones over here. These sensors basically measure stroke with respect to a frame that is fixed, that is not moving, right? So this is quite a challenge, and it's something that needs to be considered probably in future studies. Measure the position in Cartesian space is quite difficult. Right now, we're using sensors like LVDTs or linear potentiometers because we can create an electrical signal that we can feed back that into a microcontroller and run some calculations to try to predict the exact position in space of the specimen. But that's very difficult to do. So in order to try to calibrate our external system, we use a contactless external sensing system, for instance, using a camera, and we can measure our estimates of our external measuring system and contrast those with the ones given by cameras. And through a calibration process, we can try to minimize the error between the two. Ideally, we can use cameras to try to get better measurements in Cartesian space. That will be excellent. But remember that we need to run this in real time, so doing image processing could take some time. So finally, we have the identified system, like the one shown here. This is a multi-axial loading assembly where we have multi-inputs, which are the multi-commands to each actuator, and multi-measurements that are basically the sensors installed on each of the actuators or the Cartesian degrees of freedom that we want to measure. There is a problem in maRTHS, which is multi-actuator dynamic coupling, and this is basically following the same study provided by these researchers in early 2000. If we have, for instance, the problem of Darby et al., where we want to impose both displacement and rotation in one point, we need two actuators. Ideally, we will have that these two Cartesian coordinates will be uncoupled. So what this means, basically, if we want to command only pure translation, the measurement of that translation will be given by a transfer function H11, right? And also ideally, if we only command pure rotation, this pure rotation, the measurement will be a function of a transfer function H22. There is no interaction between rotation that I command and translation that I measure. This is the ideal case. But in reality, there are coupling and crosstalk effects between these two coordinates. And this coupling effect worsens the tracking problem, the synchronization problem that I explained before for a 1 degree of freedom system with one actuator. So multi-actuator dynamic coupling must be considered when designing compensators for maRTHS tests. The way we do this is through the construction of a model of the system using system identification procedures. So we got an input signal that is measured. We collect data from the measurements of our system, and then we create a black box model where the parameters are obtained through an optimization procedure in order to get a good estimate of the outputs given the inputs. So we try to estimate the best MIMO transfer system using this information while avoiding spurious modes. So the order of the model is quite important. So this is quite a difficult thing to do, especially because this optimization problem is not always convex. And if you use a gradient descent approach in order to get the parameters, you can get stuck at local minima, and that's complicated. So how do we conduct system identification? As I said before, we have the system, we measure the output given some input, and we create a model and we predict the output given the input that we commanded to the system. We measure the error between measured output and predicted output, and then through an identification algorithm, we tune parameters in the model such that this error minimizes. So given the model structure, for instance, a transfer function with a certain number of zeros in the numerator and poles in the denominator, we find those parameters such that this error is minimized. And this is conducted through a series of steps. First, we conduct an experimental FRF test. Then we can conduct system identification in actuator space. Through similarity transformation, we can turn everything to Cartesian space, and then we can get a model in Cartesian space. So the first step basically consists in create a stationary random process in Cartesian space. We command a white noise as 3 translations and 3 rotations, and we can measure all the coordinates in actuator space and the coordinates in Cartesian space. And using a frequency domain H1 estimate, we can calculate the experimental frequency response function for each of these input-output pairs. Then, using the experimental FRF in actuator space, we can curve fit this data through a model where basically we will have the experimental FRF and the model that we want to fit that is parameterized by parameters theta. We calculate the error between the two, and we take the square value of this error as the objective function, and we minimize this objective function for parameters theta that will give us the optimal results. In our case, we consider that each actuator has this order, this model order, no zeros on the numerator, and 4 poles in the denominator. And the results are quite good. You can see here that in black dots, we have the experimental FRF data. And after the optimization, we can have the transfer function in red that has a very good fit with the experimental data. So this is our model in actuator space. So I forgot to mention, this is the magnitude plot of the FRF from 0 to 20 Hertz. And then we have the phase plot, which is something that is quite important because the phase is related to delay. And you can see here that the phase is not always linear, which means that the delay is not constant across the whole frequency bandwidth. So we have also a very good fit with this data in actuator space. Then if we want to get a good estimate of the transfer function in Cartesian coordinates, we start with an initial guess for our optimization through a transformation from our model in Cartesian in actuator coordinates, and we take that into Cartesian coordinates using the LKT transformation, the linear kinematic transformation that I showed before. So through this equation here, we calculated previously the Jacobians of the kinematic transformations, and through this similarity transformation, using the information of the model that we already got for the actuator space, we get the model in Cartesian space. And we use this model as an initial guess to start the optimization in Cartesian space, because if not, there is issues of getting stuck in local minima. In our case, we used optimization procedures that were gradient based. So after some trial and error, you can get a good estimate of your model that can be used afterwards for the model-based compensation. There are some issues to consider. First of all, the specimen has an interaction with the dynamic characteristics of your multi-axial loading assembly. So in this case, we have a stiff column. It's a steel bar. And this steel column creates a restriction in the motion of the platform in the vertical direction. In the horizontal direction, the FRF, experimental FRF, without specimen, which is black, and with specimen in red is not quite different. It's not too different. But if we take a look at the FRF in the vertical direction, there is quite a difference between the situation with and without specimen. So this is something that needs to be accounted every time that you conduct an maRTHS. You need a good model, including the interaction of the specimen. So in our case, to try to avoid that problem, we use this kinematic constraint relationship where we assume that the displacement due to the kinematic constraint of the specimen creates a situation where the displacement in the vertical direction is 0. So with that, we have a condensed set of Cartesian coordinates. And through this similarity transformation using the matrix J bar, we create a new initial model for the optimization, and we get back to the optimization toolbox in order to get our best result. And these are the results. So in black, this is first the FRF, the experimental FRF for the magnitude plot in decibels. And we have a frequency bandwidth from 0 to 25 or 30 hertz, more or less. So the diagonal terms means that we are commanding a certain signal. For instance, we're commanding displacements in the UX direction, and we measure that the same displacement in the same coordinate. Same for displacement in UY, rotations in RX, RY, and RZ. And you can see here that the third column associated to the vertical motion is eliminated in this process. So you can see that our initial models in blue are quite good in the diagonal terms. In the off-diagonal terms are not that good, but after the optimization procedure, we get reasonable results for the off-diagonal terms as well. This is also true for the phase plots for this model. And now we finalize this framework by deciding which approach we're going to use for compensation. There are two approaches. The first one is called centralized compensation, where basically we design a controller in Cartesian space. We decide through this compensator what are the command signals in Cartesian coordinates that goes to the IKT, and then basically everything goes as explained before. This is centralized compensation. Meanwhile, decentralized compensation means that we are going to compensate in actuator space. So each actuator will have its own compensator for dynamics. So in this case, we will design 6 independent compensators in actuator space. And I'm going to show you the pros and cons of each of these approaches. So centralized compensation. This was work done in 2017. Basically, as I explained before, everything is going to command and control in Cartesian coordinates. The architecture of our compensator is a feed-forward compensator that is basically going to do most of the work. In case of model uncertainty, we use a feedback regulator to try to reduce the error that is not taken care of by the feed-forward compensator. So as explained before, if we have a desired target in blue and the measured displacements in red, we want to minimize this error for all frequencies up to a cutoff frequency of our choice. The challenge is find optimal solution for reference tracking with sufficient robustness margins in this problem. As an example, if we have a single input, single output problem, only one actuator, this is quite simple and trivial. If we want to have that the measurement will be equal to the reference or the desired target, what we can do is design a compensator, KFF, such that the system in series of the compensator and the plan that we want to control will have an open loop system, L, that will have a unit gain and 0 phase for all frequencies. So basically that means that R is equal to Y and there are no dynamics whatsoever. So what will be the ideal solution for KFF? Well, the inverse of our control plan. So if we have our feed forward to be the inverse of J, this is basically unity. And that will be a good way to approach this problem. Graphically, in a body plot, in magnitude and phase plots, the blue signal is the FRF of our control plan, of our actuator with the specimen. The red curve will be the transfer function of our feed forward. So if we combine these two together, we'll have an ideal open loop system, which is the green one with 0 dB unity gain for all frequencies and 0 phase, no delay whatsoever. But this is easily said than done, especially for multi-input, multi-output systems. When we have a MIMO system, if the MIMO system is strictly proper and is a rational transfer matrix, the inverse is anti-causal. It's non-proper, means that we have more zeros than poles after we create the inverse. Also, another problem that I don't explain here is that the MIMO system must be a same amount of inputs and outputs. If not, this matrix is not square. And if we have a non-square matrix, this is an invertible. So if we have a non-minimum phase, zeros with positive real parts, the inverse is unstable. And as explained before, if the matrix is not square, if we don't have the same amount of inputs and outputs, this inverse doesn't exist. So we can only approximate an inverse-based design in order to create a feed-forward compensator. The way we approach this is, instead of strictly get the measurement equal to the reference, we only want an approximation of the reference for the measurements. But the same approach is valid here. We can calculate the open loop gain as it's shown here in green. Our approach is that now the gains of this matrix should approach to unity gain and 0 phase for this matrix. And the steps basically it's a procedure where we have the information from an experimental model analysis. We get experimental FRF, so we can get the experimental FRF of our inverse of the system. And afterwards, we can conduct a parametric system ID to try to obtain a good transfer function for the model of the feed-forward compensator, the inverse of our model. The transfer matrix has the following structure. In each component of the matrix, we have 4 parameters, A, B, C, D. And then the pure differentiators, because basically this is a non-proper system, are non-causal, sorry, non-proper, can be implemented in real time through finite differences approximations. So we use a backwards difference approach, such that using the information of the trajectory, the desired displacements, and using tap delays, we can approximate the higher order derivatives using information of the current step and previous steps in time. And with that, we can command the feed-forward command to the multi-actuator system. Then the regulator is designed using an LQG LTR controller, where basically we calibrate the LQR and Kalman filter using a heuristic given by the loop transfer recovery procedure in order to get some performance that will give us some robustness into the controller. But this is easily said than done, because it is quite difficult, especially when you deal with multiple coordinates. And I'm not going to go into too much detail. So after you design the controller, everything is perfect. You implement this into your real-time controller, and then you can get ready for the first test. This is the prototype structure that we use in this study. It's basically a frame with 2 bays and 3 columns, 2 beams. We choose the column on the middle as our experimental substructure, and the rest is numerical. And we commanded, just for this proof of concept, a pure translational motion of the top point of the specimen. This means that if we want to impose large displacements of UX, means that all actuators must move. So this is quite important to remark. And this is a video that illustrates the problem. You can see that the motion is primarily in the X direction. All the other coordinates are commanded to be 0. And we're going to see what are the measurements if we effectively measure 0 displacement at those degrees of freedom in Cartesian coordinates. One way to assess whether our RTHS or maRTHS has a good synchronization performance is through the synchronization subspace plot. This is a graphical procedure to assess for any synchronization errors. So let's say that we have a coordinate u, and we have the target displacement u and the measurement displacement. And if we have perfect tracking, perfect synchronization, no error whatsoever, we will have a set of points that lay into a line that has a slope of 1 to 1. So basically means that each point has a measurement that is equal to the target. This is perfect tracking. But in the case of error in our setup, we will have a synchronization error that is given by these ellipses. And the difference between the blue and the red curve is a measure of the error. But more importantly, this hysteresis or this ellipse, the width of the ellipse will give us a quantity of the delay. And the principal component of this ellipse is has a slope that is associated to undershoot. If the slope is less than 1, we have undershoot, or if it's greater than 1, we have overshoot, which is something that is also quite nasty and we want to avoid. So from the experiment that I showed before, we, with a lot of care, we conducted a test without a compensation installed. And you can see that the black curve, which is the data from the experiment, has a large delay related to the width of the ellipse, and considerable undershoots given by the principal component of these results. Meanwhile, if we use model-based compensation, the delays and the undershoots are minimized. And this is quite a good result for compensating for the delays of all these actuators moving at the same time. This was done for the El Centro earthquake in 1940, scaled to 3% of the peak ground acceleration in this test, because we are working for a small scale and version of the test. Here's a figure showing the time history response, where if we can zoom in one of the peaks, the black curve is the target signal. The blue curve is the command, and basically a feed-forward compensator will always lead the way of the target. We will try to predict the future, and will always be before the target, such that the measurement will try to be as close as possible as the target displacement. So this is a result that is quite good. And if we take a look at the measurements on the other Cartesian coordinates, they are not zero, but they are extremely small. For instance, we have the other translational Cartesian coordinates, uy and uz, that in this case are probably less than 0.4 millimeters, 0.04 millimeters, which is extremely small. And in the rotations, we have also that the rotations are probably less than 0.06 degrees, which is also a quite small rotation in that sense. So with that, we say, okay, this is perfect. We can run maRTHS tests in Cartesian coordinates that have stability guarantees, and the accuracy is proved to be quite good. We can go further, for instance, for Northridge earthquake, scale to 10%. We have displacements that are on the order of 10 millimeters. This is like half of the capacity of the LBCD equipment. No compensation, very bad results. With compensation, we still have some good results with some errors due to this slight delay at the pulse load reversal of the ground motion. And this is primarily associated to the hydraulic capacity of the pumps and the all the hydraulic equipment that is used in this test. So it's not necessarily related to how we design the compensators, and in this case, it's basically a problem of constraints or capacity of the loading equipment. And in this case, we also ran the test with a nonlinear behavior for the steel column. So this approach also accommodates nonlinearity on the specimen. I can tell you that in the case of nonlinear behavior with a softening phenomena, it's a good situation, because it means that the interaction with the specimen and the actuators is softened, and less specimen interaction means that the system will behave better. So this is not a problem to deal with. Finally, decentralized compensation. So we talk about centralized compensation, and the main problem of centralized compensation is quite difficult and complicated to achieve. So in this publication, in this paper from 2020, it was published like a couple of months ago, we proposed a version of maRTHS where each of the actuators are compensated individually. So you can see here the numerical and experimental substructures, and we use blocks to translate from Cartesian to actuator coordinates and vice versa. But each of these blocks, for instance, the N to P block, have kinematic transformations, but at the same time has compensators for each of the actuators individually. The other thing that was considered to try to avoid this problem of getting errors on our predictions using only LVDTs is that external potentiometers were installed to try to get displacements or positions of the moving platform. And using those external potentiometers, we tried to predict what was the best extension of the actuator to design the feedback regulator of that particular actuator. The details are presented in the paper, but basically this is the idea. We command signals in Cartesian space, in actuator space, and for each actuator we have a controller where we want to minimize the error between the measured signal of the actuator and the desired signal for each actuator. Not only that, we designed for each actuator a modified version of the model-based compensation, where we design a feed-forward filter to get unity gain 0 phase for the open loop transfer function. But we created a feedback filter on top of that open loop gain in order to try to reduce the error in that unity gain 0 phase estimation of the open loop system. As an experimental validation, we use the same test setup, the same still column, but in this case, we consider 2 degrees of freedom on the boundary of the column, 1 translation in X direction, and 1 rotation. And here are the results. Basically, no control, large delays and large errors in the synchronization subspace plot. But when we installed the feed-forward compensator or the modified model-based compensator using this feedback regulator, we got reasonable results. But this is only the tracking performance for 1 actuator. We need to check if if we do the same for all 6 actuators. The question that arises is, are we doing a good compensation or good tracking in Cartesian space? We're not interested in actuator space. So these are the results in Cartesian space. As you can see, these are the results for the 1st degree of freedom, translation, and the 2nd degree of freedom, rotation. No compensation, bad results. And with feed-forward and modified model-based, we got very good accuracy in the synchronization of both signals. We were interested in whether there was any elastic deformation of the reaction wall. So we installed LED sensors, and through a contactless camera, we measured the position of each LED in space, and we tried to assess whether there was any off-plane deformation of the reaction wall when we applied the loading over the specimen. So these figures show the displacement, the off-plane displacement of the orange LEDs over here. And we can see that the orange LEDs have basically deformations out of the plane that were no higher than 0.6 millimeters. And this is a time history of the deformation, off-plane deformation of the 2nd LED, which is the 2nd blue LED of the rigid box of the LBCD. So even though there is some elastic deformation of our reaction frame, these are negligible, are quite small, so still the results are reasonably good in this sense. And finally, using this more simple approach on designing compensators only in actuator space, the researcher that was conducting the test provided a way to try to include more actuators into a specimen. So this is basically the motivation. Imagine that you have a part of a structure, a subsystem, 2 columns and 1 beam, or 1 column cut in 2 pieces and 1 piece and 1 beam. And we want to impose multiple boundary conditions and multiple points of this large system. This was done previously by Mahmoud et al. In 2013, but for hybrid simulation slow speed. So we wanted to run this test using multiple boxes and multiple actuators. So this is all these figures and results that I'm going to show next are courtesy of Amirali Najafi, who is a PhD candidate at the University of Illinois at Urbana-Champaign, working under the supervision of Professor Bill Spencer. So the main idea here is bring this framework for multi-axial RTHS to try to solve this problem of how to conduct maRTHS with multiple boxes. Now, in this case, we have 12 actuators instead of 6. And the idea is the same. So we have a numerical substructure, and we will command a signal in actuator space to each box independently. And then basically we will compensate each actuator independently. We will get the information of each of the specimens independently, and we will feed back that into the numerical substructure in terms of the forces that were measured. The example that was shown here as a proof of concept was a curved bridge with 3 piers and a curved bridge deck, where 2 piers were selected to be experimental substructures or physical specimen. The rest of the structure, the deck and the 3rd pier, was modeled numerically and compiled and run in real time in the controller, microcontroller. So for this purpose, we had to, or the researcher had to choose a different microcontroller because the previous one didn't have enough inputs and outputs channels to do all the calculations and generate all the signals from digital to analog and vice versa. So a new microcontroller based on SpeedGo was provided. And through this microcontroller, we have now multiple channels to connect to all these actuators and run the test. And this video here, courtesy of Amirali, shows the test, the real test in the laboratory, where this figure on the top left corner shows the numerical substructure. In red, you can see the numerical substructure, the deck, and the 3rd pier. Meanwhile, the blue lines show the position of each specimen in the laboratory. So this is a center earthquake with both components of ground motion, the principal direction and the orthogonal direction. No vertical acceleration was imposed in this test. Give me a second because I think my presentation stopped. Okay, sorry about that. Let me go back. And regarding the synchronization errors, both LBCVs show very good synchronization tracking of all the Cartesian coordinates, but not taking into account the vertical motion. The vertical motion was considered as a kinematic constraint, so was removed from this simulation to conduct the test. So this is one challenge for the future, is try to maintain that displacement, and on top of that have a mixed mode method to also enforce gravitational forces over this maRTHS approach. So in conclusion, maRTHS framework is a cost-effective alternative to shaking table tests, allows for realistic assessment of rate-dependent structural systems. This framework was implemented and validated using a small-scale setup. The model-based compensator effectively reduces tracking errors for maRTHS testing. And the experimental results show good performance for test specimens with linear and nonlinear responses. We have pros and cons for both this centralized and decentralized compensation. For centralized compensation, this is based on Cartesian coordinates, and we have direct control of the specimen motion center, what we want to control in Cartesian space, on the space where the specimen is located. But it's difficult to implement because we need to run system identification and model-based compensation in Cartesian coordinates, and this is quite difficult to achieve. can accommodate errors from reaction frame flexibility and joint slippage. So this is considered in the development of this framework, of this approach. Meanwhile, the centralized compensation is based on actuator coordinates. We have indirect control of the specimen motion center. It's easier to implement and have a lot of capabilities to try to include more complicated setups with more actuators, etc. But the errors from reaction frame flexibility and joint slippage are not totally avoided. So this is something that needs to be considered when you take this choice of designing with this approach. For future work, we would like to explore more about mixed mode displacement force control for MIRTHS. We would like to not only design the compensators to impose displacements, but also we would like to accurately control a vertical degree of freedom where we want to prescribe forces, for instance, gravity loads. This is something that it's not done, it's not ready yet, but this is something that we would like to explore in the future. And finally, everything has been done as a proof of concept in a small scale facility, but in the future, we will be very delighted to try to bring all the knowledge, the tools developed in this small scale facility and implement it in this large scale facility like the one available in the University of Illinois or on the other facilities that I showed previously. For that, it is required to have enough loading capacity in terms of the hydraulic equipment, considering hydraulic accumulators for large flow demands to have enough pressure to move the actuators and move the column of oil at the velocities that are required by the displacements that are demanded. And on top of that, we need manifolds to add additional fast response to each of the actuators. I would like to acknowledge Professor Bill Spencer for his support on this research, and Amirali Najafi for also his support in the first part of the centralized compensator. The decentralized compensator is part of his doctorate studies. And I also like to acknowledge his contribution in this presentation. Also, I would like to acknowledge funding agencies that supported my studies, Becas Chile, Fulbright Scholarship, and the Newmark Endowed Fund from the Civil and Environmental Engineering Department at the University of Illinois. And with that, I would like to thank you all for attending this webinar, and I will be very delighted to answer any questions that you may have. Thank you.
Hello, Gaston.
Christian, hi, how are you?
How are you doing? It was a very nice presentation. I'm sorry I was late. I have a quick question though. Can you elaborate a little bit more about the identification technique that you use? You said that you have to do model updating with a identification at all times. So can you maybe mention something about what type of technique you're using in this step of your project? Thank you.
Yeah, thank you, Christian. The identification is a critical aspect. As I explained before, we use this experimental FRF approach where we collect data from a modal analysis test. And with that data in the frequency domain, we use an optimization algorithm to get the parameters that best describe the response that we collect from the lab. This procedure is not an easy task to do, especially because the objective function that you want to minimize is not always, as I said before, it's not always convex. So if you change the initial guess for your parameters and run the optimization, you can get stuck in local minima. And you change the initial guess or the initial point again, and you get another result and another result. So this is quite difficult to achieve, especially in Cartesian coordinates. In actuator coordinates, it's not big of a deal because the order is small. We are curve fitting the data to a system that has 4 poles, no zeros. So for each actuator is very simple, but in Cartesian coordinates it's quite hard to do. So to get the best initial guess, we use this idea of first getting the best model possible in actuator coordinates, and then we obtain an initial model through a similarity transformation using the information that we get from the kinematics. But those kinematics are linearized kinematics. So this initial guess, it's only valid for that particular operation point. So yeah, indeed, this is a challenging problem to solve. But sure, probably there are different approaches to system identification that can be implemented to try to make this method more rational, like using time domain approaches for system identification. This is an alternative, but that has not been considered, at least in the current stage of this research.
Thank you very much. That was very clear. Thank you.
Thank you, Kristen. And also one thing that I think Kristen mentioned, I explained before that specimen interaction is quite important. And you can see that for a soft specimen, probably interaction is not too large. Stiff specimens will create a lot of dynamic coupling. So if you want to have a good assessment of your dynamics that you want to compensate, you need to install the specimen and include the interaction of the specimen in your system identification procedure. If not, you are going to have a completely different model, and that model may not be suitable to design compensators and control all these dynamics that are appearing because of this interaction, which makes this much more complicated than before.
So what you're saying is that you have to consider the interaction, like the transfer system planned basically interaction, but don't we always consider that? I know that there are some cases where we don't, but in the majority of the cases we do consider this interaction, right?
Yes, we do, and that creates a big problem because every time that you want to do a new test with a new specimen, you need to run system identification all over again.
Right.
And previously, it was time consuming to run system identification only for one actuator with one specimen. Imagine now having to deal with all these channels and run this optimization that could take hours or days to try to get the best set of parameters that will give you a good model. And on top of that, then you need to design your controller. So this is something that I think there should be a more rational way to try to get good controllers to run maRTHS, and will be like a turnkey solution so everyone can run maRTHS without too much knowledge of the specimen interaction or the dynamic coupling of your loading assembly.
Thank you.
Thank you, Kristen. Johnny has a question here. Could you explain how this approach is suitable for nonlinear specimens if the identified model is based on transfer functions? That's a good question, Johnny. Unfortunately, the framework right now is based on a model of the system, which is a linear version of the model. there are several sources of nonlinearity for this system. The first and probably the most important one is the geometric nonlinearity. It's due to the fact that you have large displacements. The system is highly nonlinear, right? The second source of nonlinearity can be associated to the dynamics of the actuators. The actuators exhibit some hysteresis and there's friction, etc., etc. And third, the nonlinearity of your specimen. Yeah. In this framework, we only consider a linearized version of the model, and we design compensators based on that linearized model. But even though the feedforward is designed for this linearized version, if there is some uncertainty in the model that is not captured, we still have this second layer in the compensator that gives enough robustness to the controller. In MBC, in the model-based compensator, we use an LQG with LTR, and it was tuned so that the loop, the shaping of the open loops transfer function has some properties that we deem to be appropriate in order to run the test. Meanwhile, on the decentralized version of the problem, we use this modified MBC, where we installed a regulator on top of the open loop system between feedforward and let me show you, between the feedforward and the control plant. I think this is broken, no matter. But then again, in that modified model-based version, we also add some robustness due to uncertainty. The uncertainty basically is due to the fact that we are dealing with a linearized version of the model, and we're not including all the non-linearities that may affect the dynamics of the problem. Fortunately, if there is a large nonlinearity due to the inelastic behavior of the specimen, this will always serve as a way to have better performance, because inelastic behavior is usually has a softening behavior, and that will decrease the specimen interaction. So the coupling will reduce, and with less coupling, the actuators will behave better to encompass the displacements that are commanded by the microcontroller. I don't know if that answers your question, Johnny.
Yes, thank you, Gaston, completely.
Thank you, Johnny. I don't see any more questions. Does anyone have any other question before we close the webinar? I know that this is a quite difficult topic, but the details on this presentation are found on the references that I presented in the different slides. So if you want to know more about this research, you can have a look at these references. And obviously, you are more than welcome to contact me or contact Amirali, who done the second part of this presentation for more details about this procedure. Let's see if there are more questions before we end the webinar.
Oh, hi, Gaston. I have a question.
Yes, Alejandro, hi.
Hi, so I understand that the amount of actuators depends on the capacity that you need for the simulation, but is there any specific configuration that it's easier to control, or that yields like better performance?
That's a good question. It's very interesting. That's related more on the design of the loading assembly itself, right? So in my presentation, I showed different approaches of loading assemblies with multiple actuators. The first and most used in our discipline is the mass configuration, which is this cruciform platform with 8 actuators. And these 8 actuators were chosen such that you impose the displacements and the forces in a certain way, right? Why 8 and no 6? Well, that's basically the approach of the University of Illinois by designing the load and boundary condition box. You need only at least 6 actuators in order to have a parallel manipulator, a redundant system, in order to impose a 3-dimensional rigid body motion at one point. If what you are looking for is imposing less than 6 degrees of freedom at one point, obviously you can have a loading assembly that has less actuators. The less amount of actuators and the simpler your kinematics are, the less challenging the system identification and the dynamic compensation will be. So you will be in a more advantageous point in that sense. Every time that you increase the number of actuators, the difficulty on compensating the dynamics of your system will increase dramatically, right? So if you go to your lab and you found that you have some equipment that can be used for this purpose, the first question that you need to answer is whether you can arrange those actuators to create a loading assembly that will have some capabilities in terms of displacements and force. Given that, then you need to decide how you're going to orient your actuators such that your kinematics are not too difficult to solve. And those kinematics will have some restrictions and constraints as well, will not be able to reach all positions in Cartesian space. If you want to reach multiple positions in Cartesian space, you need more actuators. So those are the key components or aspects that you need to consider every time that you want to design a loading assembly. And after designing your loading assembly, then you need to have sufficient hardware for real-time execution and all the algorithms that we discussed in order to run this kind of test.
Thank you.
Thank you, Alejandro. Let me see. Any other question? Sunny, who is helping me organizing the webinar. I don't know if there is a time we need to close the webinar.
I don't think there's any specific time, but if there are no other questions, then yes, we can call it a day.
Okay, so if there's further questions, please contact me through email or my Twitter account or my website. You can find my email there. You can send also your questions to Max, and they can send me your questions and I can answer them, no problem. And yeah, basically that's it. I appreciate your participation and attendance, and I would love to discuss with you further about these very interesting and challenging topics. Thank you.